So yeah, so we left out in the last class, we defined stress transformation for 2D planar bodies, right? And we said there are three unknowns in a 2D planar body: sigma x, sigma y, and tau xy. So two normal stresses, one shear stress. The reason for being one shear stress is the complementary shear stress are same, right? So we know the directions. Directions are defined. Only thing the value is you have to find out. So the value comes out to be, or one of the direction will give the other three directions, right? And value for one will give other three values. So all these shear stresses can be known by only one shear stress. And we also understood that a shear stress can be represented by a matrix of 2 by 2 for a two-dimensional system or two-dimensional planar bodies. And then we said that transformation of stresses are very, very important because the directions that you are looking at with the XY coordinate may not be the direction where you get maximum stresses, right? And the system or the member or the material can start failing from any other direction apart from the directions of your regular X and Y coordinates. Therefore, it becomes very important for an engineer to understand the values of stresses and the direction of stresses along the 360-degree orientation of the material point, right? And for that, we need to have stress transformation. So you transform stresses from one plane to another plane. And for this, you need to know at least the stresses at one of the planes, right? So if you know stresses along one of the plane, that means the three values along one of the plane, you can transform it to any other plane you want. And for that, we use formulas. The formulas are given by sigma x dash and sigma y dash. Let's say they are the two different planes. This is sigma x dash and this is sigma y dash with an orientation of angle theta, right? So if there is an orientation of angle theta from your regular plane, this is my regular plane, and the orientation is angle theta here, then the stresses in the transformed coordinates plane are given by sigma x dash is sigma x. That means the stress in the regular plane plus sigma y is the stress in the perpendicular to the regular plane, this one, divided by 2, and then this sigma. Remember, there is a cos 2 theta. Please note this. Do not forget it. Okay. This is very important. It's not cos theta. It is cos 2 theta for orientation of theta degree plane, right? Please note. Okay. So for an orientation of theta degree angle anti-clockwise, you have cos 2 theta coming into your equation of transformation. Similarly, tan 2 theta, right? So it depends on double the change in angle. Similarly, sigma y dash also we found the relationship. I have uploaded these notes last class, yesterday itself, so you could have gone through it. And while doing it, you get two kinds of invariant. One invariant is the trace of the matrix is constant. That means sigma x dash plus sigma y dash is equal to sigma x plus sigma y. Right? So this is constant. And that should be equal to sigma x double dash plus sigma y double dash for any other plane. So any plane you take, this should be constant. So that should also be equal to sigma principal 1 axis plus sigma principal 2, right? Maximum principal and minimum principal. Also, we said that this was an interesting finding, that if you make sigma x dash minus the average stress along a plane and then add square of tau and shear stress, you get it to be a constant. And that constant is, r, we call it radius. We'll call it radius because this plus this, so this is, let us represent this as a variable. So let's say x square plus y square is equal to r square is what you get here. So, and that's our equation for a circle. So sigma x dash minus sigma average whole square plus tau x dash y dash square, it becomes r square, and that should be equal to again sigma x minus sigma average whole square plus tau xy whole square should be equal to r square. So that's also another constant that you get, and this is a constant for a circle. So sigma x dash and tau xy are actually points on a circle with radius r, right? And center sigma average comma 0, right? So I will write it as sigma x dash and tau xy dash dash are points on the circumference of a circle, right, with radius r and center, because these are the two things you need to draw a circle, sigma average, which I can write as, if you want me to write, you can write better way, that sigma x plus sigma y by 2, right, comma 0. All right, so we got a circle, and if you can draw that circle, I know a circle can have 360-degree angle orientation, so I know that every point around that point 360-degree I can find stresses. So that's the whole objective, to draw this circle. So how do you draw this circle? We draw this circle, nothing can be rubbed here, okay, so we draw this circle. So this is the formulation of the circle, right? This is the formulation of the circle, okay. So the center is sigma average, that means sigma x plus sigma y. Let's say this is, whatever, sigma x plus sigma y by 2, that is this point, and tau, so we put one is sigma axis, this is your sigma axis, positive sigma axis, sigma x axis, and this is your tau x of the axis, okay, right? So this is your tau xy axis, and therefore your circular radius starts with 0 at tau, so this will be on this line, and it will be at sigma average here, right, some point, some point here, and your radius is r. So you know the radius value is given by this formula here. R square is, R square is sigma x minus sigma y by 2 whole square plus tau x by whole square, right? So this is your R, sigma x minus sigma y whole square by 2 and tau x. So that because you will be from the reference plane, you can get sigma x and sigma y and tau xy in the known plane, right? This is the plane, so I will know these values here, right? So one of the plane will be known, and that plane will give you that R and sigma average, right? So once you draw this, you draw the radius, and then you can draw the circle. Once you have drawn the circle will cross your x-axis or the sigma x-axis at 2 points, let's say A and B. One of them will be higher value, one of them will be lower value. The lower value is called minimum principal stress, and the higher value is called maximum principal stress, because that's the highest stress that the material will, the highest normal stress that the material will have, right? So you can see that no value is higher than this in normal stress. There is no normal stress value higher than this. So this is the highest value, and there is no normal stress which is minimum value than this, right? So these are the two principal stresses, principal normal stresses. Similarly, you can find maximum shear stress, that is this one, right? And which will be equal to your R. So your maximum shear stress is equal to R. And at maximum shear stress, your sigma value is the average. The normal stress value is the average normal stress. Okay. Any point you take on that circle will represent this normal stress as this one and the shear stress as this value, right? For an angle which is 2 theta, remember that, not theta, 2 theta. The angle is 2 theta. Okay, because this circle is drawn based on 2 theta, not based on theta. So this angle is 2 theta. So therefore 180-degree opposite is actually 360-degree. Okay, and 90-degree is actually in plane, is actually 180-degree in your circle. This circle is called Morse circle. We'll learn to draw Morse circle in the next class, but I'm just giving you a hint that there is a circular representation from the analytical formulation itself. And in the next class, we'll learn how to draw this Morse circle and how to analyze that Morse circle and how to find stresses from the Morse circle. So this is your Morse circle, right? Can we rub something here? Yeah. Thank you. Yes. So this is your Morse circle. So let's say, yes. So this is the plane here you have. So this is your sigma x. This is your x-axis. This is your y-axis. So let's say we know sigma x and sigma y, right? So from that sigma x and sigma y, you can find sigma x plus sigma y by 2, and that point will be your center point. And also you can find the radius, right, by sigma x minus sigma y by 2 whole square plus tau xy whole square root. that will give you r, and then you can find radius. So once I know the center and I know the radius, from that values I will draw this circle. Now let's say I've been asked to find orientation at an angle theta p. Okay, so how much I will go here? I will go theta 2p here, right? Instead of theta p, I will go theta 2p, and if I go theta 2p, I'll get to a point like this, let's say. Then I'll draw a line, and this is my point of the stress. I'll draw a vertical line, so that's my sigma x, okay, and this is my shear stress tau xy. All right, and how do I find sigma y? I will draw a 90-degree angle, a 180-degree angle. This value will give me my sigma y. So I will know it. Okay, and you might be asked also to find principal stresses and the orientation of principal plane. So this, if this is your normal axis, that means your sigma x and sigma y, tau xy, this is the value. So this is your theta 2p, right? 2 theta p. So 2 theta p is this orientation angle for your going to your principal axis. So that divided by 2, this angle divided by 2 will give you your orientation of your p, maximum stress, principal planes. So this is your maximum principal plane stress. This is the minimum principal normal stress. Okay. So sigma max and sigma mean are given by sigma x plus sigma y by 2 plus minus the radius. Okay. All right. So you can find that, and once you can find it, and the orientation angle is given by this form. Right. So coplanar principal stresses are also said. There are few discussions given here. These are important discussions. Please note them. Okay. Let's do let's solve a problem. Okay, something also is given. Maximum shear stress plane is always theta s plus 45 degree. Okay, theta s is your this is your 90 degrees. So this is your maximum plane of shear stress. So that is going to be your principal plane. It will make a 90 degree with the principal plane, 45 degree with the principal planes. Okay, in the actual orientation, it will make a 45 degree. In mode circle, it will make a 90 degree with your principal plane. This is your principal plane, and this is your maximum shear stress plane, right? So it makes a 90 degree in mode circle. 90 degree in mode circle is equivalent to 90 by half, which is 45 degree in the actual material plane, right? But there will be another angle from your xy axis, because your xy axis may not be your principal planes. So that will be theta s plus 45 degree. All right. Anything more I have to say? Nothing. Let's solve one or two problems. Okay. Let's look at this problem. State of plane stress shown in the figure. So this is a figure that has been given to you, and its state of stress is given, right? So sigma y is given as 10 MPa compressive. You see the arrow is bottom downward, so it's compressive because both of them are pushing the material, trying to squeeze the material. So that's compressive stress. And along x, it is tensile stress. So that's my x and y. Okay. Along x, it is tensile, right? Because it's trying to pull. That's given. Now it has asked determine the principal planes, principal stresses, maximum shear stress corresponding to normal stress, and the corresponding normal stress. Okay. These are the things we have been asked to find. Let us understand this figure. So this is the figure that is drawn. There's a point Q around which these stresses are found. We know the stress along x is given 50 MPa. Shear stress positive is given tau xy, and there is 40 MPa, and negative sigma y is given as this. So I can write them as sigma x is positive 50 MPa, sigma y is negative 10 MPa, and tau xy is positive 40. Done. It's fixed. These three are given. Now I've been asked what will be its principal planes. Right? We just found the formula for principal planes. Where is that? Yes. Sigma max and sigma min values will be given by this. I know sigma x, I know sigma y, I know tau xy, right? I can put that and I can find this. The plane for principal planes will be given by tan theta s, tan 2 theta s will be minus of sigma x minus sigma y tau xy, right? So I can plug those values in because those values are known to me. Now these values are known to me. I'll just plug them in. So first, the plane, principal plane, right? So for principal plane, tan of 2 theta is 2 tau xy by sigma x minus sigma y. So you come out to be h, and this come out to be 80 by 60. Okay, that is found. Now for this tan inverse, I will have two angles. One is tan 2 theta p will be 53 degree, and another one will be 180 plus 53, right? Because there will be two values within 360 for which tan will have same value, right? 80 by 60. These two. Okay. And then the plane, in plane, material plane angles will be 26.6 degree and 116 degree. So this divided by 2 actually. So okay, 2 theta p divided by 2, and this also divided by 2, you get this. Now there is 2 theta p. Why there are 2 theta p? And each one of them is 90 degree apart. Why? One of them will represent maximum principal direction. The other one will represent the minimum principal direction, right? If you see the Morse circle, they are 180 degree apart from each other in a Morse circle, right? And if they are 180 degree apart in Morse circle, in plane, in material plane, it will be 90 degree apart, right? So that's why you get two planes. One is 26 degree, the other one is 160 degree. All right. In matrix formulation also you can write this. Please find the eigenvalues and eigenvector of this matrix. The eigenvector will represent these two angles. Okay, and eigenvalues will represent the stress values. We can find the stress values now. The stress values will be sigma max and sigma min will be this, and you plug in the values. Once you plug in the values, you get 70 MPa and minus 30 MPa is the sigma mean. Negative value meaning it is on the left hand side of the Morse circle, and that means it's a compressive. Okay, positive means tensile, because we have assumed positive to be tensile and negative to be compressive, right? And along the principal planes, what will be its shear stress? Can anybody answer? What would be the shear stress on the principal planes? The radius. On the principal stress planes, let's say, let us look at this is the principal plane stresses. What is the shear stress value at these planes? 0, no?
0, yes, sir.
It will always be 0 for principal plane. The shear stresses will be 0. Universal. Okay, I have written them here. Read them. So they will be 0. So shear stress is 0. Now if I need to draw the axis, draw the plane. Okay, how do you draw the plane? This is the plane that is drawn here. So now I have theta p is 26.6 degree. Okay, so 26.6 degree. So what I'll do is, first, how do I draw it? First, I will draw my xy axis. This is my x axis, and that's my y axis, right? I need a x dash y dash axis which makes 26.6 degree about this axis. So that may be this one. This is theta p 26 point something, whatever is there. How much it is? 26.6. Okay, it's anti-clockwise because it has come positive. Positive is anti-clockwise. Remember that we drew it anti-clockwise. We keep saying that it is anti-clockwise, that is positive. And now I have to draw the plane, right? So the material plane. So that's going to be your material plane. Okay, I know sigma x is positive maximum. So this is your sigma x. I know compressive is tensile. So this is going to be a tensile compressive. And they are principal planes, right? So I'll write it as sigma p1, and I'll write it as sigma p2. And the values are also known to you. One is 70 MPa, and the other one is minus 30 MPa. The sign is already given, so I will not write minus 30 MPa. I will write it. Okay, and there is shear stress that is 0 because principal plane doesn't have any shear stress. So that's your. This you have to draw in exams also. In exams, in tutorials, everywhere. Just finding the stresses is not enough. You have to draw the plane and show the plane. Okay, so this is the drawing. I have shown you now. I'll show it again in the next class. I'll show you for 3-4 classes. but ultimately you have to try practicing. All right. Now let's look at shear stress, right? The third question is maximum shear stress. The formula for maximum shear stress is the radius itself, right? So this is the radius, and that comes out to be some value, 50 MPa. And we know that maximum shear stress is going to make 45-degree angle with the principal stress plane, right? It's going to make 45-degree angle with the principal stress plane. It can be positive 45, it can be negative 45, doesn't matter, right? It is both side 45. How do you know both side 45? You go to the mode circle again, yeah. So this is your principal plane, right? One of them is this, one of them is this. This is maximum principal plane, this is minimum principal plane. You see the shear stress plane, which is this one, makes a 90-degree angle. Again, this is a shear stress plane, which also makes an angle 90 degree. So it will be, in mode circle, it will be plus minus 90. In material plane, it will be plus minus 45 degree. So I will just do addition or subtraction of 45 degree. So the planes will be minus 18.4 degree and 71 degree, right? These are my maximum shear stress plane. And you can draw the plane also. First you have to draw this axis. Then you have to draw the deformed, the oriented axis, the changed axis, transformed axis, and that for that the angle will be 18.4 degree. It's from here, right? Minus, so it's clockwise. Minus meaning it will go clockwise. So this is clockwise, and once you get clockwise, you can find the shear stress value. We have found 50. We can give 50, and you see the shear stress value is positive, so it's going to go like this. Okay, and then this, this. We have to find the normal stress also in this plane, because normal stress will act at that plane. And what will be the value of normal stress? Let's go to the mode circle and find out. For a shear stress plane, maximum shear stress plane, the normal stress value is the average value, right? And the average value is, if you remember, it's constant. It is sigma x plus sigma y by 2. It's also sigma p1 plus sigma p2 by 2, right? So we can just find it based on that. You see, it is written sigma x plus sigma y by 2, and it comes out to be 20 MPa. Let's do it from here also. 70, plus of minus 30 is 40 divided by 2 is again 20 MPa. So this plus this divided by 2, or sigma x plus sigma y divided by 2 will give you the same value. So it is 20 MPa. So you can now, and it's positive, right? So it's going to be tensile. All right. So that you got. And this will also be tensile, 20 MPa. All right. Why is that is going to be tensile? Because if you see again, go to the mode circle. So that gives you an easy understanding, the mode circle, that this is one of the shear stress plane where it is same in normal stress. This is another shear stress plane, normal stress remains same. It doesn't change its sign. Okay. So it's going to be the same in both cases. And that's here. Okay. With that, I'll stop. You might have another class. Please go through the stress transformation for the second problem yourself. There are a few notes I've given here. Please read these notes. These are very important for you. And with that, I'll stop. We'll have more on mode circle in the next class. Thank you very much for attending and staying so long. Thanks.